Thank you everyone for joining part 1 of this webinar on floating point computation traps and pitfalls. Just a quick reminder, part 2 will follow on this Thursday, so the day after tomorrow, so make sure you register to that as well. I'm Lavinia Battaglia, the customer service representative here at Bagsang, and our speaker is Roberto Bagnara, who is CTO and chief scientist at Bagsang, other than a very passionate computer science professor at Parma University. Not only, Robert is also a member of the Mr. C Working Group and of the International Standardization Working Group of the C programming language. Before we start, please note that you can write all your questions in the Q&A section on the left of your screen. Please do so throughout the entire webinar, so at the end we can read the questions straight away and use that time to reply to as many as we can. All right then, let's turn this over to Roberto.
Okay, thank you very much, and let us start immediately. So here is the outline for today's presentation. We will start observing that floating point numbers are very different from real numbers. I will have to introduce the IEEE 754 binary floating point standard because a proper understanding of this one is crucial for understanding the rest of both webinars. And I will go on to a section where I will show that floating point arithmetic is very different from real arithmetic, and in particular that most property we tend to assume from numbers in general do not hold for floating point numbers. And not to let you feel depressed after having presented you with problems, I will also start presenting some solutions, even though for the solution part 2 of the webinar is the main one. Okay. So I have done part of the work that is presented here with several colleagues at Bagsang and elsewhere, and I have also borrowed ideas and material to prepare the slides from a number of subjects that you see listed here. So let's start with the first part. So here we have a small program written in C, where the objective is to print 1/10. So we compile it, we execute it, and we obtain 1/10. So we are happy. But okay, this is not, this is an illusion. And we can see this if we change the program a little bit. So we have added the part in red. We have added 0.27 before the F format specifier. And now we can see that the number we print is no longer 1/10. It's different from 1/10. The part in red is new. What happens? So two things were misleading. So the first one is that we are working with binary floating point numbers. So 0.1, 1/10, is not exactly representable in this number family. And the other problem that that misled us was the fact that printf with a %f specifier prints 6 decimal digits. So, and the 6 decimal digits let us think that this was really 1/10. And in reality, when we print more digits, we see that this is not true. So this is trivial. Let's start with, let's go on with something more complex. So here we have another small C program, which computes x plus a into y, x minus a into z, and then it prints the difference between y and z. So it does x plus a minus x minus a, and this should be equal to 2 times a. And since a is initialized to 1, we expect an output of 2. We compile, we run, and we obtain a very different number. It's not 2, So it's a large number that is completely different from what we expect. Now, let us change just one digit in the value of x. You see? So it was an 8, the last digit. Now it's a 7. We changed only one digit, and the rest remained the same. We do the same computation as before. We compile, we execute, and we do not obtain 2. Again, we obtain 0. Or better, we obtain a number that prints as 0 if we only print 6 decimal digits. Let's change the program again. So one would say, okay, but this is because you declared y and z float. So quite likely this will be IEEE single precision. Let us move to double precision for all variables. So we declare all the variables of double type, and we change the initial value of x, and we get 1. So it's not 2, it's 1. So floating point numbers are behaving in a very different way from real numbers. Let's go on with another example. Suppose that we want to compute the term of index 20 of this recurrence relation. Okay, so A0 and A1 are defined directly, and an plus 2 is defined in terms of an plus 1 and an. So working on the real numbers, we obtain this, that a closed form solution for this recurrence relation is given here. So it's clear that the terms with base 6 dominate. So this, as n approaches infinity, this sequence approaches 6. And A20 is almost equal to 6. So we code this in C. This is a literal conversion of the formula we have seen in the previous slide in C. So, and we print the term of index 20. We expected a number that is very near to 6, and we obtain 100. So one might say, okay, let us increase the precision. Let's here we have float variables, so single precision. Let's go to double. Better, let's go to long doubles. Okay, same problem, same program with long double variables. We do not obtain 6, we obtain 99.99 and so on. So things did not improve very much. So a common scenario when you talk to people using floating point numbers and you ask the question, how do you know that the answer provided by your program is adequate? They are of various kinds, so I've tried to summarize them on this slide. So some tell you, what do you mean? And other would say, hey, we use double precision, so we have very precise computation. And other would say that we always get this answer. Other would say that others get that answer. And some would say, we did several tests, and this is by far the best answer to the question. Let us move on and observe that floating point errors can cause serious damage. Probably the most famous one is the Ariane 5 fiasco, which was due to an overflow in a conversion. So this was a very, very expensive software bug that costed a lot of money. And luckily, it did not cost the life of anyone. So now it's time for a short poll. So do or did you use floating point arithmetic? Okay, so let's see the answer. Yes, I have used them, including in critical projects. Or yes, I used them, but in non-critical parts of project. Oh no, we use fixed point arithmetics. no, there was no need for it. And the last one is no, we were forbidden to use it. In some industry sectors, simply floating point numbers cannot be used. So this is one possible answer.
Okay, so we've got 36% yes, including in critical projects, 39% yes, but only non-critical or parts of projects, 10% no, we used fixed point arithmetics, 12% no, there was no need for it, and a little 3% no, we were forbidden to use it.
Okay, this is very interesting. So let's continue. Let's move to the IEEE 754 binary floating point standard, which improved things considerably. So before this standard, there was huge variability in the floating point number implementation. So things have improved much. So let's first introduce the binary floating point format defined by IEEE 754. So a floating point format is uniquely identified by two natural numbers. P is a number of significant digits. P stands for precision. So, and since we are talking about binary floating point formats, we are talking about binary digits. And Emax is the maximum exponent. So, and the minimum exponent is obtained from the maximum one by taking E min equals to 1 minus E max. So the three binary formats defined by IEEE 754 are called binary 32, binary 64, and binary 128. So in binary 32, it's also called a single precision format. We have 24 bits of precision, and the maximum exponent is 127. In moving to binary 64, double precision, we have 53 bits of precision, and the maximum exponent is 1023, so we have also an extended range. So how are these numbers represented? So let's start with the proper numbers. All the signed zero and non-zero numbers are of this form. So -1 to the power of s. So if the s bit is 0, -1 to the power of 0 is 1. So we have a positive number. So this one is multiplied by 2 to the power of the exponent, which is multiplied by the mantissa. The mantissa is a base 2 decimal number in this format. So there is the first digit, D0, and then an implicit decimal dot, and then the D1, D2, so P minus 1 digits. And the number M is obtained as the sum from I that goes to 0, from 0 to pi minus 1 of DI, the ith binary digits, multiplied by 2 to the power of minus I. So these are the ordinary number. The only strange things here is that there are signed zeros. So we may have that M is 0, and the sign can be positive or negative. We will deal about signed zeros very shortly. In addition to these numbers, we have non-numbers that are represented in the format. We have a symbolic representation for the infinities. We have plus infinity and minus infinity, and a symbolic representation for data called NaNs. Nan stands for not a number. There are two varieties of NaNs. Quiet nuns are propagated by most operation and without raising exceptions, whereas signaling none can cause a signally invalid operation exception. We'll go through them later. So given this representation, we can identify on all the floating point formats different spatial quantities. For example, we have the smallest positive normal floating point number. called f nor min, which is 2 to the power of the minimum exponent. The maximum finite floating point numbers is this one, 2 to the power of Emax multiplied by this factor. Okay, there are non-zero floating point numbers whose absolute value is smaller than the smallest positive normal floating point numbers. We will talk about them. These are called subnormals. They are called subnormals because, differently from the other numbers, which are called normals, they have always fewer than p significant digits, so they are less precise. Okay. Note that the signed zeros plus 0 and minus 0 are distinct floating point numbers. So let us now illustrate these things about numbers and non-numbers. Notice that in this talk and in the next one as well, I will give emphasis to the C or C++ programming language. They are basically the same as far as floating point numbers are concerned, but all what is said applies to most programming languages. And also another important thing about notation, when I write plus with a circle, or minus with a circle, or dot with a circle, or slash with a circle, I denote floating point addition, subtraction, multiplication, and division. And the circle is used as a reminder that they are different, very different from ordinary arithmetic operators that are defined on the real numbers. So why do we have signed zeros? Why do we have plus 0 and minus 0? There are several answers. So it's to preserve the sign in case of underflow. We talk about underflow when a very small quantity is replaced by 0. It was so small, and that it was the most precise approximation is 0. With signed zeros, at least we preserve the sign. So plus 0 means something that is very small but positive, and similarly for negative 0. And by doing this, we can preserve mathematical identities across discontinuities. For example, 1 divided by 1 divided by plus or minus infinity is plus or minus infinity. Okay, this is an identity that works in real numbers also for non-infinite numbers. So it works in floating point formats defined by IEEE 754, also for plus and minus infinity. There are simpler implementations for some classes of algorithm, especially in complex arithmetic. For example, the integer logarithm of a complex number. So let's say Z is a complex number, the real part is X, the imaginary part is Y, and X is negative. Okay, then since the limit for Y that goes to 0 from plus or from minus of the complex logarithm of Z is plus or minus pi, then it is reasonable to define the logarithm of X plus 0i as plus or minus pi. So, and this is true for other algorithms. So notice that plus 0 and minus 0 compare equal. So if you, in a program, you use the equal operator in order to compare two floating point quantities, and one is plus 0 and the other is minus 0, then the comparison will give true. However, the substitution property of equality does not hold. So in real numbers, if you substitute something with something that is equal to it, the result doesn't change. This is not true in floating point numbers. So for example, 1 divided by plus 0 is plus infinity, which is different from 1 divided by minus 0, which is minus infinity. Okay, even though plus 0 and minus 0 compare equal. So the behavior of signed zeros is tricky. the rule of signs for multiplication and division is respected, but for addition and subtraction, things are more complex. So let us examine the first three lines. These are the easy cases. So if x is different from 0, then if you add plus or minus 0 to x, well, you obtain x, which makes sense. Then let us look at this line. So minus 0 plus minus 0. It means I am adding something that is very small but negative to something that is very small but negative. I obtain something that is very small and negative. Okay? So minus plus minus, minus 0. Plus 0 plus plus 0 is plus 0. Okay? And things become more tricky for subtraction, and they are also dependent on the rounding mode, which is current. So we will talk about rounding modes very soon. Okay, so why do we have infinities in this IEEE 754 numbers? The reason is to silently handle overflows in arithmetic operation. So we have an overflow, we have the result of an operation that is too large to be represented in a decently approximated way. And so we use infinity in order to represent this overflow. Another reason is to represent the result of a division of a non-zero number by 0. Okay, so since 0 means a very small number, 1 divided by 0 is infinity with a proper sign, as we have already observed. Note that infinities in floating point numbers, as in mathematics, they are not numbers. Another thing that people tend to assume, and it is not true, is that infinities do not necessarily approximate very large numbers. Okay, so if we take the log f function, so it's the logarithm, natural logarithm function defined on a single precision number, we have that log f of plus infinity is plus infinity. However, this plus infinity might come from 10 to the power of 39. So it's not surprising that 10 to the power of 39 was replaced by infinity here. However, we obtain infinity as a result, even though the real result was around 90. So this infinity stands for 90, which is not a very large number. Okay. Notice also that infinities are not necessarily propagated throughout the operations. For example, 1 divided by plus infinity is plus 0. And final observation, infinities can easily lead to NaNs, so not numbers. Why do we have these non-numbers? For example, in addition, why we have non-numbers in addition to the infinities? So there are several reasons. So first one is to represent results of operation without a meaningful result on the reals. So 0 divided by 0 is not a number. Okay. In plus infinity minus plus infinity is also not a number, and the square root of minus 1 is not a real number. So this is the first reason to have NaNs in the floating point binary formats. There is an important reason concerning performance. So you need not do error checking at every step of your computation. You can do it just at the end. Okay, so if you only use operations that do propagate NaNs. So you do the computation, which may involve several operations, and then you check the final result, whether you obtained a NaN or not. And if you obtained a NaN, hopefully you have a plan B to implement. There is a reason concerning performance. With NaNs, code can be vectorized without changing their behavior. NaNs can also contain extra information. This is called the payload. and this is normally used to encode the reason why a NaN was generated. And in most operations, if the result is a signaling none, an exception is raised, and then a quiet none is propagated. Nuns also have disadvantages. So nuns, and similarly for infinities, these results are lost when converting to integers. It's worse than that, actually. They are undefined behavior. So if you try to convert a none to an integer in C, it's undefined behavior. And similarly, same thing for infinities. Okay. All comparison operation involving a none give false. In fact, one of the possibilities to check if a floating point value is none is to compare it with itself. If you write if x equals x, and this gives false, it means that x is none. It compares different to itself. And another problem with nuns is that, as I said, they can contain payloads. However, when you do a binary operation on two nuns with different payloads, only one of the payloads is propagated. This is an implementation defined aspect. And also there are some operations that unfortunately fail to propagate non-inputs. For example, if you use the standard library function PO, which is meant to compute approximation to the power function, 1 to the power of nan and nan to the power of 0, these give 1. Rather unfortunate choice, because this spoils one of the possibility I have illustrated in the previous slide. So I do my computation and I check the result for none only at the end. Well, if you use PO or other floating point library function, this doesn't work. Okay, so we have signed zeros, infinities, and nuns. One thing that is important to understand is that they are all needed to ensure closure of operation. So in this slide, we summarize what we have. So if I divide x by plus infinity, I have plus 0. So having plus infinity brings us to have signed zeros. And on the other hand, if we have signed zeros, then we need signed infinities. However, if we have infinities, then we need nuns, because plus infinity minus plus infinity is none. It's the only sensible solution. Okay, so we need the entire thing in order to have the closure of operations. Closure means that any operation, any floating point operation is representable somehow in the floating point format, even though with none or with an infinity or with a signed 0, something that does not exist in real numbers. Okay, so why do we have subnormals? I have said before that we have numbers with less precision than a p number of binary digits, and these are called subnormals. They are there because they allow for gradual underflow. So one thing that it is not obvious from the definition of the IEEE 754 floating point formats is that the difference between 0 and the smallest normalized number is much larger than the difference between the smallest normalized number and its successor. This means that there is a hole around 0. Okay, and so even though subnormals have less precision than normals, giving a subnormal is more precise than underflowing to 0. And for example, without subnormals, the following code can have surprising result. You see, there is a test that in the intention of the programmer is meant to prevent division by 0. So the division is done only if A is different from B. However, if we don't have subnormals, A can be different from B, and when you compute the difference, this can still give 0 because subnormals are not there. So you get an underflow, and this is a division by 0. Okay. However, subnormals have their share of problems. Typically, the problem is a problem of efficiency. The machine that I'm using to give this webinar is a machine equipped with an Intel Core i7 processor, and subnormals are up to 2 orders of magnitude slower than normal numbers on this machine. On some machine, they are implemented in software. So whenever one of the arguments is a subnormal, then the language implementation traps to service routine, which does the operation in software. So this is the reason why on several implementations, they can be switched off. So there is a control bit in the floating point unit that you can set to say, I don't want subnormals number, because I don't want, because subnormals are generated, a sudden slowdown up to 2 orders of magnitude. However, you should be cautious. That's why you have the option. Do not forget the previous example here. So without subnormals, this thing will not have the desired effect. Okay? So let's now move to rounding modes. The floating point arithmetic operation are defined to behave as if the computation was executed on the reals, and then the result is rounded, so to fit the floating point format in question. And there are several rounding modes. In C, there are 4 floating point rounding modes that you can select using the function fe get round from the floating point environment header file. So downward rounds towards negative infinity, to nearest rounds to the nearest floating point number, towards 0 rounds towards 0, so the negatives are rounded up and the positives are rounded down, and the upward rounding mode rounds towards positive infinity. Okay, there is one thing that one could ask here, rounding to the nearest, what does it mean when the number, the exact result is exactly halfway between the predecessor and successor floating point numbers? Here there are 2 possibilities. One is tail to even, which means one of the 2 neighboring floating point numbers will have an even mantissa, and this one is chosen. And the other possibility is rounding away from 0. One of the 2 will be more distant from 0 than the other one. Okay, so let's see an example. I use the standard function round to integer to explain the rounding modes. So I'm not, this function does something different from rounding floating point numbers. It rounds to the nearest integer. And however, this function obeys the rounding mode in force. So you see that this small program sets the rounding mode to all the values I've mentioned in the previous slides, and then it converts values that are not integer to see how they are rounded. So here is the output. With downward rounding mode, minus 1.5 is rounded to minus 2 because we are going down. We are going towards minus infinity. And so 3.5 is rounded to 3. To the nearest, this is interesting. So minus 1.5 is halfway in between minus 2 and minus 1. But minus 2 is even. So this is the one that is chosen. And similarly, 3.5 is halfway in between 3 and 4. However, 4 is even, so 4 is chosen. Rounding towards 0, minus 1.5, 0 is up, so it's rounded to 1, minus 1. And 3.5 is greater than 0, so it is rounded towards 0, down, so it's rounded to 3. Rounding up is easy, so minus 1.5 goes up to minus 1, and 3.5 goes up to 4. So the standard function we have used for the experiment are int rounds to nearest ties to even. There is another one, which is called round, which implements round to nearest, but ties to away from 0. Okay? So floating point exceptions. In IEEE 754, there is a definition of 5 exceptions that can occur, and using the C standard terminology, they can be raised during floating point computation. When exceptions are raised, 2 things can happen, and this is programmable by setting a bit in the floating point unit control word. So by default, what usually happens is that the exception is simply recorded, and the fact that there has been an exception can be recovered by reading the floating point status word. So, of course, if you read it before it is overwritten, okay? And the program continues with a default value. What do I mean by a default value? Plus infinity, for example, or not a number. Okay, we will see this in the next slide. There is also the possibility to enable traps for exceptions, and in this case, the program receives a signal. So let's see what are these 5 exceptions. So one is called invalid operation. And this is raised by all operation resulting in NaNs, not the numbers, conversion of NaNs or infinity to, or 2 large values to integers, order comparison involving NaNs, and so on. The division by 0 exception is triggered by division by 0. The default value is plus or minus infinity, as we already observed. Overflow is when the result is too large in magnitude, and the default value is either plus or minus infinity or the maximum floating point number. This depends on the rounding mode. For example, if you have an overflow and you are rounding down, you choose the largest floating point numbers. If you are in other rounding mode, then you choose plus infinity. Underflow, as we already said, is when the result is too small to be calculated accurately to produce normalized numbers. So default value is plus or minus 0. If we are in flush to 0 mode, we have said that we can disable subnormals, or it can be a subnormal approximation. And the 5th and last exception is inexact, which captures all the cases of overflow plus all cases where the rounded result is not exact, where some approximation has been done. So enable floating point exception has a few advantages. So you can detect errors in try-catch blocks. So with some language support, you can do something like you can do in C++ with try-catch. And using a debugger is easier because the debugger will give you control as soon as an exception has been raised, and so you can inspect the variables and see exactly where the exception occurred. However, there are many more disadvantages. So handling traps is complex and potentially inefficient. If you do not trap, if you do not trap a signal, you can obtain a crash in your program. Some compiler optimization are inhibited. In particular, vectorization may be inhibited. Or if you do vectorization anyway, then the code may behave differently when vector instructions are used. Okay, and in particular, multiple exception may result into just one trap. And also, a CPU with out-of-order processing must use speculative execution when traps are enabled. Why? because in order to keep the pipeline full, it will have to do instruction, look ahead for instruction, but these instructions that have been executed might have to be backtracked if later is discovered that a trap has been generated for a previous operation. So exceptions are problematic. So let's now go into floating point anomalies. So the observation that will be deepened in next webinar, in part 2 webinar, where we also will see more solutions, is that of the properties we know about rational numbers or real number, little is left. Okay. So basically, we have some closure with the help of symbolic representations for infinities and NaNs, and we have commutativity of addition and multiplication, plus the fact that the changing of sign is a precise operation. For example, we don't have associativity. So it's very easy to understand that if we add 3 numbers, x, y, and z, it is very possible if we do x plus y and the result plus z, we may obtain infinity, even though doing x plus the sum of y plus z does not give infinity. Okay, and the thing is not only, the phenomenon does not only happen with when infinities are generated, so because of overflow, but also because of absorption. So we will talk about absorption in a minute. And so this is when a large operand, for example, in an addition, is when a large operand absorbs a small operand. For example, here we have 10 to the power of 20 plus 1. Well, if we do the 1 plus 10 to the power of 20, 1 is absorbed into 10 to the power of 20. So the result is 10 to the power of 20. And so when we later subtract minus 10 to the power of 20, we obtain 0. Whereas here, if we associate differently, first we compute 10 to the power of 20 plus minus 10 to the power of 20. Here we obtain 0, and 1 plus 0 is 1. So you can see that we obtain very different results. What is the identity element for plus? One would say plus 0. No, plus 0 does not work, because minus 0 plus 0 is plus 0. So plus 0 does not behave as identity, otherwise we would have minus 0 here. Okay, so minus 0 is instead the identity for plus. However, if we treat it as an identity, then we would be tempted to say that we have the inverse. However, we don't have the inverse if minus 0 is the identity. You see, there is no number x for which plus 0 plus x gives minus 0. And of course, we don't have distributivity. So distributivity, I mean, almost everybody knows that we don't have distributivity on floating point numbers. So what do we have? We have that 1 multiplied by x, or x divided by 1 is x. So at least this, okay? However, x divided by x may be different from 1. For example, if x is 0, or if is infinite, or is a NaN. As I said, the changing of sign operation is exact. So x minus y is the same as x plus minus y, at least this. And the good news are finished. So all the rest is bad news. For example, x minus y is not the same as minus y minus x. So if you try 1 minus 1 is plus 0, but minus 1 minus 1 is minus 0 in round to nearest, at least. Okay? So x minus x may give something that is not 0. 0 times x can give something that is not 0. X minus 0 may give something that is not x. And minus x can be different from 0 minus x. Okay, there are examples here, and I have no time to go through all of them. So let's talk about absorption, because I will need this in one of the solutions I giving in this part 1 webinar. As I've said, absorption occurs when the result of an arithmetic operation is equal to one of the operands, even if the other one is not the neutral element of that operation. So, for example, for addition, we have that y plus z is y, but z is not 0. So z was absorbed into y in the addition operation. And of course, the thing is symmetric here. So we may have y plus z equals z without y being 0. This is absorption for the addition operation. For subtraction, we can have absorption because we have that y minus z is y, but z is not 0. So z was absorbed into y in the subtraction operation, and also the other way around. So y minus z might give us minus z even though y is not 0. Again, absorption in subtraction. We can have absorption also in multiplication. We have that y times z is equal to plus or minus y without z being equal to 1 or minus 1, and also symmetrically the other way around. For division, we talk about absorption when we have that y divided by z is plus or minus y, but z is not plus 1 and is not minus 1. So again, z was absorbed into y in the division operation. Okay, so let's look at another example showing a further issue with floating point numbers, for which we will illustrate one possible solution. So the problem is with the equality operator in C. Here we have an example, and now that you have seen the introductory example, I think all of you will understand what is wrong here. So as soon as you see this 0.1 here, you say, 0.1 is not exactly representable here. So if we reason on the reals here, when we do A plus B plus C, so minus 1 plus 0.2 plus 0.9, okay, this should be 0.1, okay, but we are not in the real numbers. We are on floating point numbers. So the program output is somewhat surprising, not for you, because it prints that 0.1000 is equal to itself. And you know why? Because printf is printing only 6 digits after the decimal dot, and still they come what is printed is different. Even though they are printed equal, it's different because they are different because of approximation. Okay, so we have seen many problems. Can we start seeing some solution? Yes, and next webinar we'll see more solution and also some more problems. Floating point comparison. So you should never compare two floating point quantities using the equality operator of C, unless for very special cases. For example, you want to know if something is exactly 0. This can be admitted, okay? But for most application, you shouldn't even ask yourself if they are equal. Very often, if they are equal by chance. You want to know if they are close to each other, where close to each other depends on the application. So the one possibility is doing a test like this. So you compute the difference between the two quantities, and you ensure that such a difference is smaller than or equal to this quantity. So there is a tolerance E, okay, multiplied by the maximum of 1, the absolute value of U, and the absolute value of V. So this is a nice trick, ensuring that when U and V are small, smaller than 1, absolute tolerance is used, because you see here the maximum will be 1. Okay, so you will have an absolute tolerance. When U or V are large, then relative tolerance is used. Okay, depending on the application, you may want to use different tolerances for the absolute and relative cases. So the formula is slightly more complex in this case, but still manageable. And what should you choose for the E tolerance? It depends on the application. If you want a standard solution, you can choose the epsilon of a given floating point format. So this is defined in the C standard. I am quoting C18 here. There are 3 standard macros: FLT epsilon for single precision floating point, double epsilon, and LDBL epsilon. Then this is defined as the difference between 1 and the least value greater than 1 that is representable in the given floating point type. The expression is the base, so in our case is 2 to the power of 1 minus p. So for the single precision IEEE 754 format, this would be 2 to the power of minus 23. Let us code this idea. So here we have written a function in order to avoid using the built-in equality operator, which is called very close. And we use this trick of coding the first of the expression I've shown, using FLT epsilon as the tolerance, and the output, as was expected, is that the two numbers are very close. Okay, let's see another nice problem which has a very nice solution. So let us say that we want to compute the sum of numbers. So in this example, I am taking the sum from k that goes from 1 to 10 to the power of 6, so 1,000,000, of 1 over k squared. Let us say we want to compute it in single precision. The correctly rounded result is here. So if we code this naively in C, so we are naive, we know nothing about absorption, so we code exactly as written here. And the computed result with this implementation has only 4 digits of the result that are correct. So the red ones, so 1, 6, 4, 4 is okay, and then there is a difference in this in the next digit. So we can improve things. What's happening here? What's happening here is that we have absorption. So we start summing large number, and then we sum smaller and smaller numbers. So when we go up, the chances of absorption are higher, and in fact we do have absorption. So in this revised program, we simply loop the other way around. We start from 1,000,000 and we go down. So we start summing the small numbers together, and we sum greater number as we go on. So we have much less absorption in this case, and you see that we have 2 more digits that are correct here. Okay, we had 4 here, And here we have 6 digits that are correct. But there are much better solutions. The only point is to know them. So this is incredibly nice. This is called Kahan summation. I'm not going through the details, but an additional variable is kept in order to compensate for the low order bits that you would lose because of absorption. And also it has the disadvantage that instead of having just one addition, you need one addition and 3 subtractions. However, the results are surprising. Even without using the trick of looping backward, we get all the digits correct. Okay, all the digits are correct. Okay, I cannot go into details here. So you go to Google and search for Kahan summation algorithm. You will find this and other very beautiful things. So time to conclude. I'm a bit late. Floating point numbers are very different from real numbers. We have had an improvement, a significant improvement from IEEE 754. Many of us do not even know how was the word before the introduction of IEEE 754. So we have illustrated a number of anomalies of floating point computation, and these are anomalies all software engineers should be aware of, especially if they are working in high integrity systems, let alone critical systems. So we have illustrated 2 concrete problems, so comparing numbers and computing a sum of numbers that due to precision loss can go horribly wrong. And for those, there are simple and standard remediation measures. So in the webinar we will have the day after tomorrow, Thursday, we will go deeper into solutions to the issue raised by floating point computation. And more precisely, we will look at what can the compiler do with your floating point C code. This is something that today we skip it completely. Today is almost as we reason it almost in assembly code, apart from printf and similar. So we will present various floating point catastrophes, so unwanted generation of NaNs, infinities, and subnormals, which we have introduced at this time. We will see non-obvious algorithms that to solve seemingly trivial problems. So we will see in particular how to compute the average of 2 numbers and how to solve a quadratic equation. And we will also go into the issue of what do standard mathematical libraries provide you with. And the spoiler is they guarantee very little. Okay, so when you print a log of something in your program, you should be aware of this. And this will be one of the topics in next webinar. So I'm now ready for your questions.
Okay, thank you, Roberto. So the first question is, are other representations for floating point number besides IEEE 754 still using current microprocessors?
Yes, there are not many. It's quite difficult to find them, and the truth is that the IEEE 754 was widely adopted, but not all parts of it. So what you have usually is that you have partial implementations of IEEE 754. There are also floating point formats that are completely different. So, for example, implementations of extended precision integers using 2 doubles. Okay, and also another thing that is quickly being adopted are half precision floating point numbers. So for applications in machine learning and similar things, the precision of single 32-bit floating point numbers is even too much, and there are much more stringent needs for efficiency. So this is why short 16-bit floating point integers are being adopted. So there is, of course, a clear way of generalizing IEEE 754 to 16-bit integer, 16-bit floating point numbers.
So next question, does the misrecoding standard cover some of the risks presented?
This is a very good question. So there is not explicit coverage of these issues. There are coding guidelines that do two things. They ask you to document all implementation defined behaviors on which your program depends, and almost everything in floating point arithmetic is implementation defined. So if you want to comply, you will have to identify these implementation defined behaviors and make sure that you understand how your implementation deals with them. And also the cases of undefined behaviors that are triggered by floating point problem are the subject of guideline rule 1.3. So, however, there is no explicit guidance. So MISRA C 2004, so the previous version had the rule saying that you shouldn't compare two floating point numbers using the equality operator. This was removed in MISRA 2012. Actually, I am a strong advocate for this rule, not because it prevents major disasters. So from what I've said, using the equality operator to compare floating point numbers is the least of the problems you might have. But if you have a program in which floating point numbers are compared using the equality operator, chances are the programmer are not very aware of the fact that they are not using real numbers. So it's a good spy of the fact that something might have been misunderstood about floating point numbers.
So next question and last one for now. Can I use some tools to verify if a given function can produce unexpected effects like absorption, underflows, etc.?
Yes, we have a prototype implementation of such an object in a.k.a. I will describe it in the next webinar, so in part 2 on Thursday. So yes, even though this is still something that is not mainstream, it's badly needed. That's why we are investing a lot of energy into developing these features of a.k.a. However, it's not mainstream because it's a difficult, very difficult problem.
Okay, thank you, Roberto, and thank you again, everybody, for joining us today. Of course, if you have more questions, you can always drop us an email at info@buxen.com. Also, if you'd like to see this webinar again or share it with your colleagues, head over to our YouTube channel. We will send you the link in the post-webinar mailing. Some of you has asked the question. In general, there you will find all previous and future webinars. So as I said at the beginning, and as Roberto has reminded, part 2 of this webinar will follow on this Thursday, so at the same time like today. So make sure you register to get a complete picture on this topic. All right then, so thanks again, everybody, and I hope to see you all later this week. Bye-bye.
Bye-bye.